you for inviting me to the first Linux Beaver conference. I was asked, so a little bit about myself. I'm a software architect for Intel. I work in the network products group. We're responsible for all of the wired Ethernet products. There's a couple of other divisions. We also do some of the stuff that is, some of you may know about the quick assist technology that Intel puts out. That belongs to our group as well, so QAT, and then there's a software-defined networking group as well. They're all part of the network products group. I've been at Intel for 19 years. Been at Intel for 19 years. So I've been around a long time. All of it has been communications related in some manner. I've been writing device drivers for over 30 years. Almost all of that time has also been communications oriented in one way or another, either at the very low end talking to hardware or up into the different stacks. Back in the day it was Unix, and for the last about 12 years I've been writing Linux device drivers. Intel doesn't pay me to write device drivers anymore, but I do review a lot of code. Our group is responsible for, there's 10 different Linux kernel drivers that we're responsible for, and we maintain all of them, and so there's lots of different changes and commits and everything else that are going on for those drivers, and basically they all come down by some of my responsibility into that. So we have a relatively large team that is responsible for all of those drivers. There are 43 people now doing commits on those different drivers. So the group is growing and large, it's relatively large. And Intel in general now has taken over the #1 position of contributions to the Linux kernel. It's always between us and Red Hat for who's committing the most commits to the kernel. Intel for the last year and a half or so has been #1 on the list, so we contribute quite a bit to that. So, DPDK. So, how many people here know what DPDK is? How many are actively using it? There's a few. Okay. Well, that's good. That's good. I'm surprised that there's this many people who know about it. So I guess we would just kind of get into this here. So DPDK. This came out of a need to have a mechanism to be able to process lots of packets. Now, as ones that are familiar with this know, there is no real stack that's kind of on top of this. This is basically just for packet processing. If you need a stack, it complicates this quite a bit. You can put a stack on top of DPDK, but then there's usually limitations with user space stacks. Stacks are very, protocol stacks are in the Linux kernel are fairly complicated because they do a lot. From integrity to different types of protocols and making sure that those protocols are being handled in a robust way. All of those things people have become very dependent on inside the Linux stack. That's really not what this is. Okay, this is for processing packets. The main use case for DPDK is for basically telcos. Okay, so telecommunication switching type products. They want to be able to handle a lot of packets coming into it. As software-defined networking becomes more important for them, one of the things that the telcos are trying to get away from is having a lot of dedicated proprietary equipment. They want to move everything onto servers that have virtualized guests with NFVs running on those guests so that they can combine a lot of functionality that they had in these proprietary pieces of equipment and move them onto a single server or multiple servers or however they want to distribute it throughout their network. This is one of the ingredients they need for being able to do that. Okay? That's why it's actually relatively important for them. As you can see, I mean, this kind of calls out everything. I don't want to go through all of this. Some of you already know, the ones that are using it know about all this already. But this gives you an overview of where we're at. The big thing here is that this is running in user space. It's all BSD licensed, so that if you add things to it, it's not viral like it is if you're running inside the Linux kernel. All of these things are important. One of the big things is that it runs as a pull mode driver, which means that it's being pulled in user space. It's one of the features that makes it perform very well. Okay. There's a couple different ways that we're going to get to later in the presentation about how the bottom end of DPDK connects to the kernel. Because obviously you need a connection to the actual NIC hardware that's actually in the system. And there's a couple different ways that can be done, and we'll talk about those individually and some of the benefits of which one's probably right for you. Everything's kind of moving toward what was called bifurcated driver. We've changed the name of that to be queue splitting. It's a little more accurate name. Bifurcation usually has to do with PCIe hardware and how you're splitting up the lanes. So we wanted to get away from that terminology. Okay. The DPDK model. So so there's a lot of people out there using it today. There's products like from Wind River. If you use their titanium server today, which a lot of telcos are using, they call it a hardened Linux. It has DPDK built into it. It comes as part of the standard product. You can configure it and use it right out of the box from them. 6Wind has products based on it too. Again, most of these things are being sold into different telcos. And it's all in how the telcos want to use it. So DPDK is one of the underlying ingredients for software-defined networking. It's a very popular product. It has gained a lot of recognition over the last 3 or 4 years. The important thing is this has pretty much kind of gone away. The kernel network interface, the KNI. While you can use that, and there's some people that want to use it, the people that are using it are becoming very diminished. There's really no need for it anymore, especially with the new bifurcated driver. The queue splitting kind of solves some of the problems that KNI was doing. And so the pull mode driver, they show it down here in DPDK. They don't really show you where you're at here, but this is all user space, and then in the kernel's down there. The interfaces to the kernel are a couple different ways, and as I said, we'll talk about the details of those a little later. Any questions about any of this? Okay. So, as a comparison, kernel bridging to L2 forwarding performance, as you can see, there's a major difference in performance by doing this, by using DPDK. We left this slide in here so that you have a good idea of exactly how many more packets are being processed. And this is one of the reasons why the telcos really like this technology. You're able to run it inside of well, for a user space, you want to have it dedicated, but you can also run them from VMs, which gives a lot of advantages for the telcos. They're able to put a lot of different VMs on a system, and as part of OpenStack, you're able to get this performance in here, and being able to process all those packets is actually quite beneficial to all the people using it. So this is really the motivation of what's going on. You have a slow path and then you have a fast path. This has been the basic UIO, which is the basic mechanism that has been used for quite a while with DPDK. There are a couple of other methods that we'll talk about for the bottom end interface to it. So really what we're going to talk about is the interface here between the kernel and user space. That's the typical Linux stack. We call it the slow path on the slide. Some people have, again, it's not a replacement for the Linux stack. I make no mistake about it, and we're not making that claim, okay? Stacks are a very important part of Linux. It's not going away. If you need all the protocols and everything that are based on the Linux stack, DPDK is not your answer, okay? There are people working on user space stacks. There are some products actually out there now that are actually doing that. However, the stacks that are being used on top of DPDK are very limited in scope. They support very few socket types, very few, in addition to the types of sockets, is the socket options. There's a storage product that Intel puts out that does exactly that. It runs DPDK and it has a stack running on top of it. But it is very limited. You can only do a few types of sockets, socket types, and a few options within those. It's highly dedicated, it's highly tuned. It does exactly what they want it to do, and it performs very well. But it's not a replacement for the Linux stack. If you're trying to do all kinds of different things that the Linux stack does today, lots of socket types, lots of different protocols, that's not what's, this is not going to get you there. You probably have to rethink your ideas if you're going to try to go down that path. One of the main tenets of this is for the bifurcated driver, queue splitting, is flow director. It's basically how the NIC can filter the packets coming into the system and get them to the correct locations, in whether it's going through the regular Linux stack or getting it up to user space. Okay? So there's lots to do with that, with the new mechanism, the bifurcated driver. And we'll talk about that as we get there. Okay? Any questions? So, some of the design principles of the new way, the bifurcated driver. Is there a question?
Yeah. So, Intel tends to present DPDK as an infrastructure for those who build infrastructure, right? That's the idea, the main idea. I mean, you don't provide all the kind of application interfaces that's presented in sockets in this, present.
Yeah.
Well, I hope you got the first. Let's cover the first part of the question.
So,
could you please repeat the question?
okay,
Yeah.
so you're asking about whether Intel is proposing.
So Intel, the goal of DPDK is to provide infrastructure for those who build infrastructure, right?
Yes.
That's the idea.
Correct.
And the overall intention is to provide those applications that lay over the virtualized, to provide the virtualized containers, hypervisors, etc. All the benefits that can be right now be done by, say, libvirt.io.
Okay. Yes, DPDK will run whether it's going to be in a virtualized guest or in like a container. That's all kind of new and kind of coming up. There's some issues with how networking and containers work today. The performance of that and the actual interface to containers themselves is kind of out of scope to what we're talking about here, but that is being worked on. One of the problems that they've been running into is the performance into a container. Trying to be able to share bandwidth with enough containers, because you can keep adding containers, and containers can be rapidly deployed. You can keep adding them, and the problem with that is you still have a limited amount of bandwidth coming out of the bottom of the sun. I didn't show it on the previous. On the bottom, right? You only have maybe a 10 gigabit interface. Everything that you're running on the system still has to go through that one interface. I mean, if you have multiple interfaces, obviously you get more than that. But that infrastructure is limited by how much you can actually get out of the system. Okay, so you are going to run into some system limitations at some point. Okay.
Mm-hmm.
Did that answer your question?
Yeah.
At least for now?
Yeah.
Okay, all right. We'll go on and then maybe we can readdress it, okay? So some of the design principles. We wanted to limit the amount of code changes that were going into this. There has been a lot. There was a number of different ways that we were going about trying to implement this bifurcated driver. And we made, I don't know, probably 6 or 8 different attempts at it. It took us, that was 6 or 8 attempts across about 2 years. There were a lot of people who didn't like some aspects of it early on. We kind of came to some consensus. We wanted to reduce the amount of code that it was. One of the problems was the early designs had a lot of code that was being added to the NIC drivers. And obviously when you add code, people get a little nervous about that because obviously per lines of code, you will end up with some amount of bugs from those lines of code that you add. And so those kind of problems kind of plagued it for a while. There was also another problem that we had to work out with the Linux networking kernel maintainer, Dave Miller. I don't know if any of you know him, but Dave's quite strict. He's a really good guy, and he had some concerns about being able to get being able to DMA from the NIC into user space. Okay. Because nothing was actually checking those addresses. There wasn't anything that was basically validating them. That's a security hole, right? Because now you can scribble over anything you want inside of memory and user space from a piece of hardware that's running inside your system. Not such a good thing. Could that be exploited? Potentially, yes. How real those threats are is unclear because you still have to have root access to be able to get to the driver and try to do something like that. While it is a potential hole, the reality of it is it may not have been as big of a deal as it turned out to be. Anyway, bottom line was they pushed back on it, and that was the last iteration before the current version of the bifurcated driver that we're using today. And everybody's in agreement that this was a really good compromise. It performs just as well as the native DPDK. And you don't have to go through having to load special drivers like the UIO driver. You can just use the flow director and some scripting. We've added some patches to the actual 10 gigabit EIX-GBE driver where it's currently implemented, and the code changes were minimal. They were less than 50 lines of code, and everything kind of worked out. It was very good. It does run in a master-slave mode, and that's kind of loosely taken. It's not like a true master where you're having conversations with the master or putting in requests to the master. Doesn't really work that way. The NIC driver by itself, once it's configured to split off the queues, the driver doesn't really do much anymore. Anything that's being filtered to those queues are going to go up to user space or go to the regular Linux stack, depending on how it's filtered or where the packets are going. So basically, this is all in the initial setup of it. Once it's set up, it just runs, and there's really no interaction between anything. Here we go. This is really the basic idea of exactly what we're doing here. UIO is what's being handled today, bifurcated driver. There's different ways of doing this, and bifurcated drivers using flow director kind of replaces exactly what's going on here with UIO, and you just end up having a queue in user space, but you still have to map the queue to the actual driver. There's some scripting that comes up. So we can talk about it on the next page. That's actually how you get this done. Let's see. I think that's all I wanted to say here. These are the startup scripts. And so this is what I was originally talking about once it's configured, it just kind of works. And it goes on, and you really don't run into very many problems with it once it's operational. and then you can run the tests. All of this code for doing all of this is in our current Linux driver that is in the upstream kernel for IXGBE, which is the 10 gigabit interface. It doesn't make much sense to run this on 1 gig. 1 gig performance is not what anybody's really looking at to be able to push packets. We're also looking at this for our 40 gigabit and our future looking 100 gigabit products. It makes more sense for everybody to be kind of concentrating on that. The same mechanism, same type of mechanism will be implemented in those drivers. So the i40E driver, which is the 40 gigabit interface from Intel, and the 100 gigabit, which is the FM10K driver. The 40 gigabit is about to get pushed. It should show up in the 4.5 kernel when the merge window opens. For FM10K, it'll be a little longer than that. It'll be sometime the first half of next year. There's some other changes going into the FM10K driver, and we're going to kind of coordinate all of that to actually show up there. But the same type of mechanism and scripting will be done for any of those drivers, and it should just work for you. When I was talking about performance, this is really what we're trying to get at. And these are all the different scenarios down here along the bottom, and the different performance that came out of all of it. And as you can see, the DPDK and the previous version, the native, well, it's called native on here, and the new version, the bifurcated driver, perform basically identically. So we've proven that this is actually a good way to go. Most people are going with the bifurcated or Q-splitting model now, getting away from having to use UIO or UIO, the IGB UIO, which we'll talk about those in a few minutes. Mostly has to do with how the interrupts were being handled. If you needed the native interrupts in the system, you had to use a specialized version of UIO that isn't upstream. That's problematic if it's not upstream, because people that are the Linux OSVs can't take that code. Okay? It has to be upstream or they can't pull it in. There's resistance to changing UIO to be able to handle those things because they're very specialized for a particular event or a particular device, and that's not something that you really want in a generic UIO interface. So those changes couldn't be pushed there, so there was really no way to make that actually happen. If you go out to dpdk.org, which is the site that hosts all of this is called out on there. There's plenty of documentation on how all of this stuff works, including some of this performance, some of the performance numbers here. Be aware that they don't actually do anything on dpdk.org. That's where they actually have the Linux drivers themselves, because they're relying on that to come with the Linux system that you're installing. Okay. Any of the more recent things, anything above about a 3.8 kernel, will get you the IXGBE driver that has this stuff in it. So. That you can run into with DPDK, at least in the past, has been head of line blocking. It's always a problem for things like this, that you can actually run into this situation. You obviously don't want to have your DPDK traffic being held up by things that are coming from the actual Linux stack and somehow slow pathing everything, right? You don't want to have to be waiting on some sort of acts or anything like that that are happening on the regular Linux stack. So you have to be able to handle this, and that's all done through the flow director. And being able to handle those situations when they come up. How many here are familiar with DCB? No? Okay. DCB is another way to be able to deal with that. It originally came up with as a need in the Linux stack, and the drivers have to interact with the Linux stack to be able to support it for FCOE. So that's fiber channel over Ethernet. Intel was a big we developed a lot of the open FCOE code that actually is available today. But DCB was one of the main factors of it. If you don't have DCB, FCOE doesn't really work very well. And it has to do with congestion and how it can get slowed down, and you end up dropping packets in a storage environment like FCOE. Dropping a packet is a very bad thing. It causes all kinds of problems, and then you end up with horrible performance on it, and obviously it's kind of defeating the whole purpose of it. So you had to implement DCB. DCB is still kind of being worked on. There's still changes going into it. After 3 years, do you think it would have been pretty stable by now? But that hasn't been the case. There always seem to be holes that people are finding that are creating problems with it. Anyway, I'm kind of getting off topic. One of the things is here, you really didn't want to be in here to dropping packets. You didn't want to be either forcing something on DPDK to be dropping the packets, or you didn't want to have this queuing problem. Okay, and so all of that had to be dealt with, and that's all really pretty much done through Flow Director. So pros and cons. The big thing is that you wanted to make sure that it performed just as well as the native interfaces. If you had something that was going to take a performance hit, a design that was going to take a performance hit, obviously that wouldn't be very good. You really had to do something that was going to be creative and meet the performance goals. You wanted to get away from using anything that was proprietary, which is KNI or the IGB UIO, because the Linux community, the distributors, the Red Hats, the SUSEs, the Canonicals, Ubuntu, anyone else, they couldn't pick it up because it wasn't upstream. So you obviously didn't want to be in that situation either. Trying to put them into that situation is basically a non-starter. You won't be able to convince any of them to be able to take anything that's inside the Linux kernel that isn't upstream, which is a very good thing. They're very rigid about that anymore. There used to be some slack in it, especially with regard to graphics drivers, but even that's kind of going away at this point. But for the networking ones and storage, there's no way that they're going to ever take anything that's outside the Linux kernel. The NIC variants, you want to make sure that if you implemented this, the change went into the one driver that's controlling the NIC. In this case, it was the 10 gigabits of the IXGBE driver. That those changes are in one location, and if the NIC supported the hardware, if the hardware was supported by the driver, then everything just works. You don't have to worry about it anymore. Everything up above it works. It's looked at as an ingredient, and in that case, everything works great. So our stuff's upstream, has been upstream for a while. This just works. There isn't any problems with it, and DPDK in this mode works great. So the one big thing here was that you're able to dynamically change things. The previous versions of all of this, of DPDK in general, you basically had to statically allocate or statically configure how many queues you were going to have going up to user space. In a rapidly changing telco environment, that's not necessarily always the best thing. It'd be much better for it to be very dynamic. And if you needed to add more queues, you're able to go in and without having to reload the driver, reload configurations inside the kernel, you're able to just do that. And with Flow Director, being able to change the rules, you're able to pull off more queues from the Linux stack and actually get them configured into to be used for DPDK. This is a much more usable model. It's much more user-friendly for the people that are basically the use cases for DPDK. So that was one of the big design goals for this, and it has come to fruition. That's exactly what we're doing today. So some of the cons, there are some slight differences between how it works for IGB, IXGBE, and other NIC drivers. However, that's really somewhat minimized. Our drivers, the Intel drivers anyway, they all pretty much do the same thing. We've designed it so that The changes that are going into those drivers basically look the same as what we've done here for IXGBE. Under the hood, there's some differences to it, but the user doesn't know that, and that's really a good thing in this case. You don't want anybody knowing any of these special things that had to be done to actually make it work right. And as I said, the I40E driver changes are going to be going in here before the end of the year, so that we're able to make sure that we're in the 4.5 kernel and the merge window modes. The other thing is that you wanted to get away from this one, which is having DPDK controlling the NIC directly. Having user space entities controlling actual system hardware is a security risk. Again, how real, you don't know, but it's a lot easier for somebody from user space to be able to be malicious than it is for something inside the Linux kernel to be malicious. And so you wanted to get away from that. And in this case, how this works, there's no chance. I mean, there's nothing that can be done by anything in user space that's actually controlling the NIC. And so you really, no matter, even if it is maliciously behaving maliciously, you really can't do anything to the actual hardware, which is exactly what you want. Okay. Any questions? Okay, so bifurcated driver. So as I said, we've pushed the patches. They've been accepted. They've been in the kernel for a long time. We're about to do it for the I40E driver, and then again for FM10K in 2016, early 2016. We've talked about Flow Director. It's the main entity that makes all of this work, and it's implemented across all of our drivers. There'll be changes that will have to go into the I40E and for the FM10K driver to actually support it, to be able to split off the queues. The Flow Director doesn't do that today explicitly, but with a small change set, we'll be able to do that. Let's see, configurations made upstream configuration acceptance easier. So the upstream patches needed to be backported to the standalone versions of the driver. Our drivers, not only are they in the Linux kernel today, but we have standalone versions of them available on SourceForge. Actually, you can get them from Intel, downloads.intel.com as well. But the SourceForge driver are basically an out-of-tree driver of what, it's a representation of what is upstream. The reason we have those, not everybody wants to be running on whatever the latest kernel is upstream. I'm sure people in this room have run into this situation. You sometimes have to you get new hardware and you want to run it on the kernel that you have today, okay? Which may be, a year or two old, maybe older. Our drivers that are out on SourceForge have a what we call a kernel compatibility module that allows that version of the driver, the very latest one, to support the very latest hardware, to run on very old kernels. We actually go back and in most cases, we can go back to a 2.4.37 kernel, which is ancient. How many in here even know what a 2.4 kernel is? A few of you, okay. Yeah, it's if you're running a kernel that's that old, you have some very specific reasons why you're trying to run it that old or on something that old. But it's also hard for you to be able to support some of the newer versions of hardware. While it may run in legacy mode, on the newer servers, you're going to run into problems. At some point, something's not going to work right. You're going to be running into some legacy type things, and it's going to be a problem for you. But anyway, I digress. Those versions of our driver will support our new hardware on very old kernels. Mostly people are using it on something like, it goes back to maybe 2.6.18, something like that, which is what Red Hat 5 was based on. So going back that far, our drivers still work. So if you buy new hardware, it works fine for our NIC hardware. You may run into some kernel things because of things like SATA drivers and things like that might not be supported, and you might have to find some updates for those kind of things. But in general, it'll generally work. And then we were talking about the changing of the name, bifurcated queue splitting. Again, bifurcation generally has to do with you bifurcate at the PCIe level. So if you have a card that is PCIe Gen 2 by 8, a lot of times it's bifurcated into two PCIe versions that are by 4. It's split up at the hardware level. That's usually when people are talking about bifurcation, that's usually what they're talking about. That's why we had to try to get away from it. We didn't really want to confuse things with the name, because we're not actually doing anything to the hardware or splitting it up at that level. We wanted to give it something that was more appropriate of a name, and so queue splitting was the one that was decided on. UIO. Generally, this works today. The UIO PCIe generic, that is in the Linux kernel today. You can use that today, but there are some drawbacks to it, mostly having to do with legacy interrupts. And so if you're using the virtual function, you can't get those interrupts, and so it causes some problems there. It doesn't actually work correctly. So you have to be a little worried about that. And then you have to use a special version of it, which is the IGB version of the driver, and that's not upstream, and so you run into that hole able to get it, and so it's better just to get away from it, and so we've done that. VFIO, so this is the other possible interface on the bottom end of DPDK. This takes on some issues. You have to have at least a 3.6 kernel for this to actually support, and that's not really the whole story. You actually need 3.8 to actually make it work correctly across all things. While 3.6 started implementing the changes that were needed to support VFIO, all of the changes didn't actually get implemented or implemented correctly until the 3.8 kernel. So if you're going to go down this path, be aware that depending on what kernel you're using, you may run into some problems there. There's some discussions on the forums that are on dpdk.org about this, so pay attention to it. If you're in a situation where you have to use a 3.6 kernel, you may want to look at that very closely. I don't know if that affects any of you, but 3.6 is getting a little old at this point, so it may not be much of a problem for people. The other big thing here is that it had to be supported by the BIOS. If you're running on older hardware, it may not have BIOS support for being able to do VTD, which is the virtualization technology that needs to go into the kernel. If VTD is not there, then you won't be able to do this. You won't be able to use this version. Now with bifurcated driver, queue splitting, this becomes irrelevant again. So there was a lot of reasons why to go down the bifurcated driver and queue splitting now, and that's really kind of where you need to be. You need to be using this. If you're involved with any of this, using this new methodology, this new mechanism will definitely help you, and you'll enjoy all the performance benefits of DPDK, and you should be okay. That's all I have. So, do we have any questions?
Yeah.
Yes.
So,
Oh, we need a microphone.
first of all, I wonder if the
Hold on a
flow.
second.
Yeah. So my question is about flow director.
Uh-huh.
Have you tried to have a TCAM-based flow director hardware instead of the software?
You have to have hardware support to be able to support TCAMs, first off. When the changes for Flow Director come out, when the changes go into the FM10K driver, which do support some TCAM support, has TCAM support in it, that should work fine for you. Okay,
So-
but you'll have to wait for and use the FM10K hardware associated with it.
So that's a new driver, right?
Yes, well, it's in the kernel today, but yes, it supports the new hardware. It's what we called, the code name for it was Red Rock Canyon, and that's our very latest hardware. It supports 10 gigabit, 25 gigabit, and 100 gigabit today. Okay, so if you buy any of those, if you buy one of those NICs, that's where you're going to go. It's a relatively expensive NIC, but it has 4 interfaces in it, and it will support what you're talking about. but the queue splitting feature hasn't been implemented there yet, but it will be in early 2016. So you're gonna have to wait a few months before it's actually gonna be there. Okay?
Thank you.
Next question.
Hi.
Hi.
The flow director, right? Which headers does it support? Ethernet, IP? Can it look into TCP and UDP headers of packets?
Yes, all of them.
So all of them, okay. And
Yeah, it's for all of them.
how many rules can be loaded into hardware? What's the typical?
It depends. Probably more than you would probably need. I'm sure that people have extended cases where they probably want more than what's available, but we haven't seen people running out of them yet. Okay, there have been some special cases where people have elaborate flow director cases, and we found ways for it to actually work today. So we have. I don't know what the limits are on it. You'd have to investigate them, and it's on by a per NIC basis, right? The IXGBE has fewer than the I40E, so if you need more, you'd probably go to an I40E interface. It still supports a 10 gigabit interface, so you'd probably be there. And then the FM10K that I was talking about has even more cases. So as we keep moving up, you're going to be able to add more and more of them, depending on the kind of hardware they're going to have. Okay?
Thank you.
Welcome.
Okay.
Any other questions?
Well, and what about not .NET? What about not .NET interfaces, like InfiniBand or something like?
Well, InfiniBand's kind of out of scope to this. I don't know of anything that's going on in the InfiniBand world or in the RDMA world that supports anything like this. This is kind of what's happening with RDMA, because it's already getting the packets from the kernel into user space, but placing them specifically in the RDMA address spaces in user space. Since that's already being done, a lot of what DPDK is used for is probably irrelevant. Also, you don't run into the situation where you have RDMA that's being routed at the L2 level, right? I mean, that's really not applicable to an RDMA interface. So some of the reasons for DPDK aren't really relevant for RDMA. Okay. So I don't know of any work that's going on for that. That is outside the scope of DPDK today. I don't know if there's work going on in the RDMA community for doing that. RDMA is still relevant. It seems to be a relatively niche market, but it does seem to maintain its own things kind of going forward, which is kind of even for InfiniBand. The next generation of servers that will be coming out from Intel have RDMA supported natively in it. So as part of the I40E driver that will be available next year for when the platform launches, it'll have an RDMA interface as well, supporting I1. Okay. Thanks. Any other question?
Okay.
Right here.
Okay.
I want to ask how this flow director can work for virtual functions, SRIV, if it's possible to control it from inside the guest systems.
Yes.
With mapped variables.
So the scripting that I was talking about that had it on there, you can actually run, one of the big use cases of this is to actually run it from guests.
From inside the guest.
From inside the guest, be able to control it, and it works fine. It's one of the big use cases for this. As I was saying, the Telcos are all running this as virtualized guests, and they're all running all of this from one of their guests, or multiple guests, as a matter of fact. Again, you start running into some hardware limits because of, no matter how many guests you have, you still have a limited pipe coming out of the actual system. So the bandwidth the queues have to be split up accordingly. You have to have some intelligence about how you're going to dedicate queues to which VMs, okay? But all that seems to work. You're able to make the configuration changes, and we haven't seen any problems with people actually doing that today.
Well, if you have lots of virtual functions, 32 or 64, but you have limited queues, so how to direct them between these areas? Do we limit it with queues available for CSIG? and how to distribute these network queues.
It's all in your configuration. Yes, you may have to play with it a bit. If you have a really complicated one where you have a lot of NFVs, okay, and a lot of NFVs running in multiple VMs, is that the case for you?
Yes.
Okay. You're going to have to make sure that you have it split up accordingly for it. You may not be using much of the native stack at all, right? You may dedicate like one queue or something going to the regular Linux stack, and all the rest can be split up between the different VMs. But it is a configuration thing. We don't know of I don't know of any limitations to it.
It's configurable and no practical limitations.
Up to the limitations of how many queues the hardware supports, no.
Okay, thank you.
Thank you.
A couple more
The next
questions.
question.
You've talked about some security hole and about DMA2 user spaces, I remember. I haven't understood quite where is the security hole, because hardware can write to physical memory, yeah, so it doesn't matter much user space, it's kernel space. It is the first question. The second one, could I/O virtualization help to mitigate this security hole?
Today, with the current implementation using Flow Director, you actually don't have a security hole. That was taken care of by that, okay, by moving to Flow Director. The previous version that we had, the address mapping, the address maps that were coming down to the driver were coming from user space. And because of that, you had a user space entity that was giving our DMA engine the addresses, which is the problem and why it was insecure. Okay, that was the basic crux of the problem. Okay, and again, I was saying that you still have to have root access to actually do some of this stuff. But if you had a compromised system, you could actually make this happen, and that was the concern by everybody. Okay, and that's why we got away with it, or got away from it. The new version doesn't have any of those security holes. There aren't any of that kind of thing going on. There is, if you're really concerned about those things, there's some work that's going on for we were talking about NFVs. One of the things that some of the telcos want is to be able to support, to have a particular NFV running in a virtualized guest that sees all the traffic coming into the system. Okay. That's a security hole. But they really want it.
If it's configured from host side, then it's probably okay.
So we went round and round. It roughly took us about a year to work out the details of this. You were able to implement something that, and it's a multi-step process. The system has to be configured for you to be able to use it, so it has to be compiled to allow it. The driver looks at that configuration and says, oh, I'm allowed to do this. Okay, so that's the second step of it. And then when the guest it allows the guest to be able to be put into a promiscuous mode to be able to see all the traffic. Okay, but as I said, the kernel has to be configured for it. If the kernel's not configured for it, it doesn't allow it. So it was a compromise, because it's still, even if you configure for this, it is still a security hole. The telco guys, they say, we don't care. We know exactly what's running on that system. There aren't malicious guests running on that system, so we don't really care that that's the case, and we need that functionality inside the VM. That's why it was implemented this way. Okay, but yes, it's still a security hole, but it's running on a protected system. They know exactly what's running on the system. The users don't really have access to it. The only software that's running on it is directly from the telco, so they're not really that concerned about it.
And as I understood, we can filter traffic between the host and the virtual machine.
Yeah.
So, in the low level, in the kernel, they said in the packets.
That's in the
Some
Flow
go
Director.
to host, some to virtual machine. So virtual machine doesn't observe host traffic, and host network stack doesn't observe virtual machine traffic.
Correct. Yes, so the guest wouldn't see things that are going to the Linux kernel. That part of it's excluded from that. That's the telcos aren't interested in that traffic. Mostly when they're configuring systems like that, they're only worried about the traffic that's coming up into DPDK. They're not worried about the traffic that's going to the regular Linux system. And typically on these telcos, other than management configuration stuff, there really isn't any traffic going up the Linux stack, so they don't really care about any of that. Okay.
Thank you.
There's another question there.
The next question.
Thank you. Let's talk technology fragmentation. You said a lot about telco companies, but what about the actual telecommunications equipment producers, developers, like Cisco? We're seeing now that they are running next to their platform hypervisor some user code in a container. Do you see any interest in the DPDK, or they're trying to do their own thing?
I don't know how to answer this. There are things going on in that space of exactly what you said that are going to be using DPDK, and these specialized users, Cisco or other switch manufacturers, basically will use DPDK, and they'll be writing applications that are on top of it. Okay, and they're going to be whatever functionality that they're supplying. You're going to see more and more of that happening, I think.
So you're saying less fragmentation?
Less fragmentation.
Yes.
Yes.
And the second part, what about NICs?
What about what?
NICs.
NICs?
Network interfaces, or network interface cards.
Yes.
Sorry. Other producers of NICs.
Yep.
Do you see any interest?
Yeah, there are. So if you go out to dpdk.org, we're not the only ones that our hardware is not. It's it's the main one. Our hardware is the main instance of everything. But Broadcom and Mellanox are very active in dpdk.org, and all of this works on their NICs as well.
Thank you.
You're welcome.
Next question.
Oh, and by the way, it's not just NIC oriented, right? There's DPDK actually has patches to actually run on PowerPC, and there's been some new patches over the last month or two to actually run on ARM as well. Now there's some functionality that ARM processors are missing. You don't get quite the same benefits that you do running on Intel architecture, but the changes are going in there with the assumption that at some point in the future, the ARM processors will have that technology, or the technology that's needed to gain the same kind of performance that you get off of an Intel processor. Okay, so we'll see how all that develops. But anyway, those changes are going into dpdk.org as well. Anything else?
Okay, any other questions?
Thank you very much.
Thank you very much for your presentation.